Good morning, everyone. This is real pleasure introducing the speaker of today's seminar. This is Dr. Carolina Kehrig. Carolina Kehrig, she graduates in physics and astronomy in the Observatorio Nacional, Rio de Janeiro, some time ago. And then she was starting her PhD in astronomy there in Rio, and there was several grants from the FAPES, from the National Brazilian Institution, but also with some grants of visiting Spain, in particular the IAA, those days by the CSIC. I don't know, maybe some of you remember the I3P grants those days. So she finished the PhD and defended at the Rio de Janeiro Observatorio Nacional 2007, and then she went after that as a visiting research fellow at the IAP Potsdam for a while. I think that was nearly 1 year or near 1 year, and then she moved to the University of Michigan with a grant. She was working there nearly 2 years, and until she won the prestigious fellowship, the Alexander von Humboldt, and then she came back to Germany and stayed working there near Berlin, and in close collaboration with people and in the institution of the AEP, the Astronomical Institution in Potsdam, where she developed I would say the central specialization of her career, which is the integral field spectroscopy in astronomy. And she was there for 2 years, and then she came back to the IAA, to Spain, with a contract under a project of excellence project of the Junta de Andalucía for 3 years. And then she moved to the Estallidos Network for, I would say, 1.5 years later, when she became the Severo Ochoa IAA Fellow. The main subject of the talk of today, which is related to the Nebular HeII emitting regions and galaxies, is very interesting in the last development of her career, and then in particular in relation to the unknown and the unsolved problem of the budget of energetic ionizing photons in this kind of galaxies. So, Carolina, this is your time. Thank you.
Thank you, Pepe. So in this presentation, I'm going to talk about the formation of the Nebula HeII line and what we can learn from metal poor HeII emitters. So why is this study of the HeII line relevant? So first of all, we need to understand that the Nebula HeII emission indicates the existence of a very hard radiation field. We need photons with energy beyond the 354 electron volts to this radiation, but in this presentation I'm talking about star-forming galaxies, where the main excitation source should be massive stars. So you can see here examples for two nearby, so the examples for spectra of two nearby HeII emitting galaxies. There you see the presence of the UV HeII at 1640 angstrom, and there you see the presence of a narrow line profile for the optical HeII. So HeII emitters are expected to be usual at high redshift, since harder ionizing spectra are predicted at the lower metallicities typical in the faraway universe. And in this sense, high ionization lines, as the HeII in metal poor galaxies, provide a useful window into the ionizing spectrum of metal poor hot stars, which are very poorly constrained from observations. And also, the Nebula HeII is considered to be one of the best traces for population tree stars, which are metal-free objects and the first generation of stars in the universe. And POP3 stars are believed to have contributed significantly to the universe reionization, which is one of the major topics in astrophysics. In this figure, taken from Tuliso and Xu 2000, you see indicated by the dotted and the solid lines the synthetic spectra of population 2 and population 3 clusters. This vertical line there represents, mark the helium-2 ionization edge. So we see that while POP2 are not hot enough to ionize helium, the POP3 cluster shows a stronger UV around the helium-2 ionizing edge. So we expect a significant transition in the ionizing spectrum of hot stars with metallicity. And from observations, we have seen that the Nebula helium-2 line tends to be stronger at low metallicity galaxies. In this figure, taken from Senchina and collaborators, we see the helium-2 over H beta versus metallicity, and it's clear that there is a trend for the helium-2 flux to be higher when we decrease the metallicity. So the helium-2 emission, by acting as a signpost of reionization era systems, it will be a fundamental piece in the era of next generation facilities where we expect to detect the rest frame UV of thousands of high ionizing emitters, including helium-2 emitters. In this slide, you see the Sloan Digital Sky Survey composite image for a few examples for metal pool helium-2 emitters. So they usually show a compact morphologies and blue, bright blue appearance indicating ongoing star formation. So regarding the helium-2 ionization, we have different sources of hard ionizing radiation that have been discussed in the literature, trying to explain the formation of the nebula helium-2 in star-forming systems. The leading candidate sources are Xray binaries, shocks, and hot Wolf-Rayet stars. Wolf-Rayet stars represent a late phase in the evolution of massive O-type stars. And here, when I say massive, I mean stars with initial mass around, so higher than 25, 30 solar masses. And despite its relevance and significant effort from observations and theory, the origin of the nebula helium-2 in galaxies, especially the low metallicity ones, is far to be a settled matter. And in the next slides, I will show you some examples where the nebula helium-2, the origin for the nebula helium-2 is still unclear. Okay, so this is a picture taken from Casata and collaborators. The black solid line shows the stack of their narrow helium-2 emitter spectra observed at intermediate redshift around 2.5. So the authors found that the stellar population models, including Wolf-Rayet stars, don't reproduce their observations, and they invoke peculiar stars that could be POP3 stars to explain the helium-2 excitation in their galaxies. When we move to lower redshifts, Shirasi and Brinchman in 2012 studied the whole sample of helium-2 emitting star-forming galaxies from SDSS, and they found that 40% of these objects don't show Wolf-Rayet features in their spectra. And they claim that signal-to-noise issues cannot be the reason for the non-detection of these Wolf-Rayet features. Some years ago, using integral field spectroscopy, we found for these two nearby metal pool star-forming galaxies that the nebula helium-2 emission is extended. It goes much beyond the location of the Wolf-Rayet stars. This is the map for the nebula helium-2 for Macquarie 178, and the location of the Wolf-Rayet stars are indicated by the green crosses. And here you have the H-alpha map for Tuesday 70. The blue crosses indicate the position of the Nebula HeII emitting spaxels, and the crosses, the green crosses again, mark the location of the Wolf-Rayet stars. So we see here that there is a spatial offset between the Nebula HeII and Wolf-Rayet stars, indicating that Wolf-Rayet might not be exclusively responsible for the formation of the helium-2. And in 2011, we performed a GMOS follow-up spectroscopy for candidate helium-2 emitting H2 regions in the very nearby galaxy M33. In this study, we found 2 new helium-2 nebula, which apparently are not associated with any hot massive star at all, and for which we still don't know what it's ionizing helium-2 there. This is the spectra for these 2 H2 regions, and you see here the presence of the narrow line profile for helium-2. A couple of years ago, these authors analyzed the UV spectra for a few nearby metal-poor star-forming galaxies. In this plot, you can see the carbon-4 over carbon-3 versus O3 over helium-2. The observations are indicated by the stars, the triangle, and the squares. And the blue dots shows photonization models powered by AGNs. Pink dots show models for shock ionization, and the orange dots represent photonization models powered by massive stars. So these authors conclude that shocks and AGNs are unlikely to provide the UV flux to explain their observations, and they suggest hot ionizing metal-poor stars as the main source for helium-2 ionizing photons. But they don't go into further details concerning this aspect in this paper. And very recently, the same authors put together optical long-slit spectra and X-ray data for some galaxies from their sample. And there you can see the SDSS U-band image for 2 galaxies among their strongest helium-2 emitters. And they found that the X-ray point-like source indicated by the red lines are too spatially offset from the optical nebular emission that they observe within the circles indicated in the figures. And based on detailed photonization models, they conclude that X-ray binaries cannot produce the sufficient number of helium-2 ionizing photons to explain their observations, and they still don't know what is ionizing helium-2 there. So I think it's clear that we have a lack of understanding of the Nebula HeII, especially in metal-poor star-forming galaxies. And additionally, most previous work are based on long-slit or single-fiber spectroscopy, which may suffer from aperture effects. So a detailed galaxy-by-galaxy study of the helium-2 emitting gas, of the properties of this gas, and their ionizing sources need to be performed. Moreover, to constrain the possible origins of helium-2 and link them to POP3 objects, the observations should target metal-poor, highly star-forming systems, which are our best counterparts of distant helium-2 emitters. So the main goal of our project is to perform spatially resolved spectroscopy of such galaxies within different epochs in the universe using worldwide integral field units. In this sense, we already published 3 articles where we show the results from integral field spectroscopy of these 2 galaxies, 1Zwick 18 and SBS 0335052A. From now on, when I refer to this galaxy, I will say only SBS because its name is too long. These galaxies are very famous objects in the extragalactic community because they are the lowest metallicity helium-2 star-forming galaxies that we know in the nearby universe at present. Just for you to have an idea, the metallicity of these objects is about 10 times lower than the metallicity of the small Magellanic Cloud. So they are our natural local counterpart of distant helium-2 emitters. We observed 1 week 18 using PIMAS IFU in Calar Alto. This box represents our field of view, which covers the main body of the galaxy, which hosts 2 main star-forming regions, which are the northwestern knot and the southeastern knot. In the case of SBS, we used MUSE IFU at the VLT, and this is a UV image from Hubble Space Telescope indicating the position of the brightest and youngest ionizing clusters in SBS. And in the next slides, I will show you our main results from these studies, which illustrate the physics that we can provide. So for 1 week 18, we find a large Nebula helium-2 emitting region, which has a diameter of approximately 400 parsec. This is the H-alpha map obtained from PIMAS, and the crosses indicate the position of the helium-2 emitting spaxels. So there you see the map for the Nebula helium-2 itself. So we can see there that the helium-2 region spatially coincides with the northwestern knot that I showed before. There you see the spatial distribution for oxygen 3 over O2, which is an indicator of the gas excitation. And when we look at this map, we immediately see that there is a trend for the gas excitation to be higher at the location of the northwestern knot. So around this area, we find a higher excitation gas, we find the Nebula helium-2 region, and also most of the higher electron temperatures, spaxels, are found there. So the observations indicate the presence of a harder radiation field at the location of the northwestern knot and thereabouts. So now let's see what we find for SBS. So also we find a highly extended Nebula helium-2 emitting region that you can see here. So this is the map for the Nebula helium-2. The white lines represent the isocontours for the helium-2 flux. And due to the higher spatial resolution of MUSE in comparison to PIMAS, we were able to perform a more detailed study of the distribution of the helium-2 in this galaxy. For example, we identified a filamentary structure that we call helium-2 shell. We also could identify 3 peaks associated with the helium-2, which are a bit offset from the brightest stellar clusters indicated that there by the white lines. And finally, MUSE data revealed that the helium-2 emitting region extends out to distance higher than 1.5 kilo2 emitting spaxels. And using this spectra, so here you can see the presence of the integrated Nebula helium-2 for 1 week 18, and here this is the helium-2 for SBS. So using this spectra, we measured the total luminosity of the Nebula helium-2 line, from which we derived the helium-2 ionizing budget, or Q of helium-2. This is an important quantity if you want to investigate the origin of the Nebula helium-2, as I will show you next, and a quantity that would be hardly derived using long-slit spectroscopy or single-fiber spectroscopy, which may suffer from aperture effects. Okay, so then now let's see how we start to try to figure out what is ionizing helium-2 in these galaxies. Both galaxies are detected in X-rays So then what we did first was to test the X-ray hypothesis. In this image, you see again the UV HST image for SBS. The white lines show the isocontours for the Nebula HeII flux, and the red and blue curves represent the hard and soft X-ray emission. For 1 week 18, you can see here the map for the Nebula HeII from PIMAS, and the red lines again show the hard X-ray emission. So while in 1 week 18, the X-ray emission is dominated by an X-ray point-like source around there, for SBS, we have the detection for X-ray point-like source there, and also some diffuse X-ray emission indicated by the white lines. And while we can see that there is some spatial correlation between the Nebula HeII and the X-ray emission, based on models, we find that the effective number of helium-2 ionizing photons provided by the X-ray emission in both galaxies is well below the observed helium-2 ionizing budget. So we conclude here that X-ray sources cannot be the main contributor to the helium-2 ionizing photons in both galaxies. So then what we did next was to test the shock hypothesis. So here for 1 week 18, you can see the maps for oxygen 1 and sulfur 2, because these are spectral features of shock excited gas. The crosses again mark the position of the individual helium-2 emitting spaxels. And we see there that basically there is no oxygen 1 emission within the helium-2 region. And in the case of the sulfur, we didn't find any significant sulfur enhancement associated with the helium-2 emitting region. So there, these plots represent optical diagnostic plots that are widely used in the literature to distinguish between different ionizing sources in galaxies. So we plot here oxygen 3 over H beta versus O1 over H alpha and sulfur 2 over H alpha. The circles and the squares represent line ratio measurements that we derived from our observations, and we immediately see that all measurements fall in the star forming region of these diagnostic diagrams. So the observations are telling us that the helium-2 region is unlikely to be produced by shocks, and massive stars should be the main excitation source. For SBS, we perform a similar analysis. So you see here the spatial distribution for oxygen 1 over H alpha and sulfur 2 over H alpha. And here the white lines show again the isocontours for Nebula HeII. So we find that there is no sign of significant sulfur 2 or oxygen 1 enhancement associated with the helium-2 emitting region. And also, when you look at this filamentary structure that I showed before that we call the helium-2 shell, we find no oxygen emission there and low values of sulfur 2 over H alpha. So then all this indicates that shocks are unlikely to be the main source of helium-2 ionizing photons in SBS as for 1 week 18. In this slide, you see again these optical diagnostic diagrams that I showed before. The open circles show measurements from individual spaxels. The red circles indicate line ratios from the helium-2 emitting spaxels, and triangles represent line ratio measurements that we obtained from integrated regions across the spatial distribution of the helium-2. But here the main point is that all line ratios, regardless the position in the galaxy, are typical from H2 regions. So, which is telling us that photonization from massive stars should be the main excitation source. So then at this point we can say that shocks and X-ray binaries are unlikely to be the main source of helium-2 ionizing photons, and hot massive stars appear at the favorite scenario. So to test the hot massive star hypothesis, we compare the observations with current stellar models applying two approaches. The first one is a more simple approach based on models of single massive stars on a star-by-star basis. And our second approach is based on stellar population synthesis models, which considers more information, more physics on the stellar population. So now let's start with our first approach, which is a more simple one. Here let me mention that despite the very low metallicity of our galaxies, we know from spectroscopy that they contain Wolf-Rayet stars. So then we started here testing the Wolf-Rayet star scenario. To do that, we compare the observed helium-2 ionizing budget with the helium-2 flux predicted from single Wolf-Rayet stars at the metallicity of our galaxies. These models were taken from Crowther and Hadfield 2006, and this comparison indicates that hundreds of Wolf-Rayet stars in the case of 1/18 and even thousands in the case of SBS are needed to explain the observations. But the point is that such a very large Wolf-Rayet population is not compatible with current stellar evolutionary models for massive stars in low metallicity environments, and it's not compatible with the stellar mass of the H2 regions in our galaxies either. And a third point is the spatial offset. So you can see here again the map for the Nebula HeII for SBS, and the crosses, these 4 crosses, indicate where the Wolf-Rayet stars are located. So here you have again the map for the helium-2 in 1/18, and the Wolf-Rayet knot is located around there. We clearly see that there is a spatial offset between the Nebula HeII and the Wolf-Rayet stars. So what we can say here is that although we cannot discard the contribution of Wolf-Rayet stars to the helium-2 ionization, they are not exclusively responsible for that. So we need to test other types of hot massive stars, assuming that the helium-2 ionization is due to stellar sources. So here let me mention that nowadays rotation is considered to be a key ingredient in the evolution of massive stars, making stars brighter and hotter. And the effects of rotation are predicted to be stronger at very low metallicities. So motivated by this, these authors published models for massive, fast-rotating single stars at a metallicity which is very close to the metallicity of our galaxies. They call them transparent wind ultraviolet intense stars, or twins. So then obviously we compare our observations with these models, and from this comparison we find that the number of twins needed to explain our observations again don't match the mass of the star-forming clusters in our galaxies. So here basically we need a cluster with 20 times the stellar mass of the star-forming regions in our galaxies. Also, we checked that these models cannot produce the highest values that we observe for helium-2 over H-beta. So, at this point, we ask ourselves what is going on in these galaxies? What is ionizing helium-2 there? As you might remember, in the beginning of the talk, I mentioned that the Nebula HeII line has been used to search for very metal-poor starbursts and POP3 hosting galaxies, because nearly metal-free stars or pop-3 stars are predicted to have a very high effective temperature and to emit a large amount of helium-2 ionizing photons. Also, observations, as I showed before, indicate that the helium-2 flux increase with decreasing metallicity. So, considering all these aspects and the fact that the other hypotheses may fail in reproducing the observations, we thought that nearly metal-free stars might be an alternative, so might hold the key to the helium-2 ionization in our galaxies. And to test this hypothetical scenario, we compare the observations with present models for rotating metal-free stars. From this comparison, we find that a much smaller number of such stars in comparison to the models considered previously can explain the observations. In the case of twins that I mentioned before, we are talking about the factor of 5-7 fewer. And we also see that the harder spectra of these models can reproduce the highest values of helium-2 over H beta obtained from our observations. Okay, so our first approach, which is based on a more simple assumptions, indicates that peculiar hot stars might be needed to explain our observations. So now let's see what we obtained from our second approach based on stellar population synthesis models. So here let me say first that most massive stars are suggested to evolve in binary systems, and binarity also is predicted to produce bluer and hotter stellar population. So then what we did, so we used grid models from the binary population and spectral synthesis known as BPAS, which considers binarity and also rotation. And to be more specific, we compare our observations with the helium-2 ionizing fluxes from all initial mass functions and the 3 lowest metallicity models available on BPAS. The 3 lowest metallicities relative to solar corresponds to 5%, 0.5%, and 0.05%. So from this exercise, we were able to check the impact on the helium-2 ionizing flux output by varying the initial mass function and the metallicity. And then let's see here the main results obtained from BPAS. First of all, the number of helium-2 ionizing photons of a binary population always exceeds that of a single star population, despite the IMF and the metallicity. None of the models with 5% solar, which is the metallicity closest to that of our galaxies, can explain the observations despite the IMF adopted. And the only 2 models that match the observed helium-2 ionizing budget are the ones with metallicity 0.05% solar with either an upper mass limit of 100 or 300 solar masses. Note here that this metallicity corresponds to approximately 70 times lower than the metallicity of our galaxies. So BPAS is telling us that while supermassive stars are not essential, a binary population and stars with metallicity much lower than the metallicity of the H2 regions are needed to explain the observation. So this is a similar result to the one that we obtained using our first approach. Very recently, Stanway and Eldridge confirmed our result. So here they plot the number of hydrogen the ratio between the number of hydrogen and helium-2 ionizing photons as a function of time. The dotted lines shows models using a salpeter IMF. And the solid lines corresponds to a more top-heavy IMF, which produce more massive stars. The purple ones corresponds to the lowest metallicity model from the past, which is the 0.05% solar, and the green lines correspond to the metallicity, the models with metallicity of 5%. This rectangle shows the range of values obtained from our observations of SPS. And we can see here that only the models with very low metallicity can explain, can reproduce the hardest ratios observed. And the authors conclude that IMF variations cannot explain the ionizing spectrum of low metallicity starbursts. So to summarize, so here you can say that traditional helium-2 ionizing sources cannot explain our observations. And when we put together the observations with state-of-the-art models, we find that peculiar very hot stars are needed to ionize helium-2 there. So our observations challenge current models for metal pool massive stars, and they are critical for understanding the gas properties and also to understand which stellar populations power this high ionization emission as the helium-2. And so we need more observations and more studies of this kind to keep moving forward in this topic. And this is what we are doing. At the moment, we are analyzing Megara data for this galaxy, which is a nearby metal pool star-forming galaxy. The data were taken during commissioning run using these 3 different gratings. So this is our field of view. And there you can see the different maps for emission lines obtained from Megara. So this is the H-alpha map, oxygen 2, O3, 43, 63, and the map for the Nebula helium-2. We have other ongoing programs with Megara. For example, we were awarded 27 hours to perform the first integral field spectroscopy of intermediate redshift helium-2 emitters selected from VMOS Ultra Deep Survey. And in this sense, we believe that our IFS studies of local and intermediate redshift helium-2 emitters might help to guide to the preparation of future mosaic data and surveys. And in this sense, we already have a mosaic project which aims to observe distant helium-2 emitters with the goal to enlarge our understanding of the primordial universe conditions. So I finish here. So this is the main takeaway points from the talk, which I'm not reading. But I hope I have convinced you of the importance of studying this metal pool helium-2 emitters. Thank you for your attention.
Thank you, Carol. Very nice talk. Now is the time for questions. So I have a question myself, but I don't want to be the first one. But anyway, I think maybe it's interesting you to elaborate why is it at all important to have a high resolution, spectral resolution, to attack the problem of the helium-2 in population 3 host candidates? Is it no high spectral resolution or intermediate or low versus intermediate to low resolution?
I think this is very important, for example, in the case of the work that we are going to do with Megara, because, for example, we are going to do a follow-up for galaxies that were observed with VMOS. So VMOS has a very low spectral resolution, I think that the resolution power of IMOs is about 200, so they don't have the sufficient resolution, for example, to disentangle between narrow and broad helium-2 components. So it's very important in this sense to really understand, so to really check if we have Wolf-Rayet stars or not in these galaxies. So especially for these ones.
Can you do a study at higher redshifts? I mean, I see there SKA, but I don't know if this is related to this question. The study of helium-2 emitters at higher redshifts.
Doing now. So we have this program with Megara.
Lower frequencies?
At the moment, I have been working on the nearby helium-2 emitters. Only nearby.
So what is SKA there?
Okay, so yes, SKA is there because one of the main science goals of SKA is understand the first source in the universe. And this is related to the helium-2 emitters, as I mentioned in the beginning of the talk.
Carol, very nice talk. Thank you very much. I have a question concerning your X-ray data that you've shown. Is it coming from Chandra? So you have good enough resolution and good enough sensitivity?
Very good. So, well, I mean, I'm not expert on X-ray, so but the spatial resolution for this Chandra data that we used is between 1.2 and 1.8 arc second.
Okay.
Good job. I have a question. What is the fraction of helium-2 emitting galaxies in the local universe?
Okay. So this is an interesting question. According to Shirasi and Brinkman, the paper that I mentioned in the beginning, so they study all the helium-2 emitting star-forming galaxies from Sloan, and what they found is that only less than 1% of all star-forming galaxies from SDSS show helium-2 emission, including nebular and broad. So when you're talking about only the nebula ones, this is for only half of this object, about 40% of this less than 1%. So it's very uncommon. And this is in agreement with model predictions, right? Because the helium-2 should be larger when you decrease the metallicity, when we have very low metallicities typical in the faraway universe. That's why the people say that they are expected to be more usual at very high redshifts.
More questions? Isabel?
So when you get to higher redshifts, you expect also to have more AGN, right? So how do you deal with having both AGN and strong subformation in lower metallicity environments at the same time? Is it possible to disentangle both?
Yes, I think so. I think there are nowadays some UV diagnostic diagrams similar to the BPT that you can use to distinguish AGNs and star forming. So using the carbon 4, carbon 3 lines, so this is possible. It's possible to be done. And this is something that we would like to do with Mosaic.
More questions? Yep.
Thank you very much for this nice talk. Despite I am no expert in this field, I think I can follow it. I had a curiosity. Could you say a few words about these populations? So, three So far as I know, this is a population of a star located in the halo, but I think it is a old population. But my question is, why these stars are poor in metallicity? Why these stars are poor in metallicity? You mentioned. Yeah.
Well, the population tree stars are defined. The term is to define the first generation of stars in the universe. So by definition, they are metal-free objects because they are the first objects formed in the universe. So that's why. But it's important, I just want to mention something here, that these stars, the existence of these stars remains entirely theoretical. So they have not been observed. So we have no observations of population tree stars. So based on the current facilities, we still are not able to get this information and to resolve individual stars. And even some present simulations from James Webb indicate that they will not be able to detect individual POP3 stars. They will be able to detect maybe some POP3 host galaxies, but not these stars in itself.
I have a question, just maybe for you to elaborate a bit, why the helium-2 line, or looking for this line, is a good trace of this kind of population-free candidates? What is the main for using helium-2?
The main reason for using helium-2 is because you can only form helium-2 if you have a very hard excitation source, which can be provided by this nearly metal-free or all-metal-free stars. Some people also have discussed the possibility of using Lyman alpha as a footprint of POP3 stars, but the problem is that Lyman alpha is different from helium, is a resonant line. So then it's much more complex to interpret the Lyman alpha photons that can suffer from scattering, absorption, depending on the geometry of the gas. So some people, some years ago, tried to use actually the Lyman alpha over helium-2 ratio as an indicator of POP3, but they decided not to use this anymore because the observed ratio might be completely different from the intrinsic one because the complexity of the Lyman alpha line.
Any more questions? If not, thank you very much again, Karen.